Hello everyone, welcome to the channel Statistica Hub. This is a course on linear algebra. In this course, we are going to cover vector spaces, algebra of matrices, ranks and inverse, elementary operations, linear equations, determinants, inner product spaces, orthogonality, eigenvalues, eigenvectors, characteristic equations, quadratic forms. Like we are going to cover all these topics one by one with the upcoming lectures. Okay, so before starting our first topic, our very first topic, which is vector spaces, before starting this, there are some prerequisites for this course. Let's see what are these topics which we need to know before starting this topic. There are relations, functions, groups, rings, and fields. You must have studied these topics earlier. We are just going throughout the basic of these topics. Okay, so let's see our very first topic, which is relation. So let's first see what does the term relation means. What does the term relations means? It is actually the existing connections among things. What is? It is the connection among things. So let's take the basic example of relation. If I say that the girl standing there is the daughter of my mother, what did I say? That the girl standing there is the daughter of my mother, then what is the relation between that girl and me? Okay, that girl is my sister. This is the relation between me and that girl, that she is my sister. Okay, this is the relation, or you can say connection. Okay, so this is the basic terminology of the relation. Okay, when it comes to the mathematical term, we need to know firstly about the Cartesian product. What is the Cartesian product? Talking about the Cartesian product, it is the set of all ordered pairs. This is the set of all ordered pairs A comma B such that A belongs to A and B belongs to B. It can be represented like A cross B. This is the representation of Cartesian product A cross B, where this is the set of all ordered pairs of A cross B, where A belongs to A and B belongs to B. Let's see it like this, that if I have a set A which have element like 2, 4, 6, and a set B which have elements like 1 and 2, and if I take a Cartesian product of these A and B, it will be like 2 comma 1, 2 comma 2, 4 comma 1, 4 comma 2, 6 comma 1, 6 comma 2. Okay, so this is the Cartesian product of set A to set B, and if I say it like the set A, which is coming from the real number set of real numbers R, and it is being Cartesian producted by the set B, which is also coming from the real number R. So this R cross R, this R cross R is the set of all ordered pairs of real numbers, which is the set of all, sorry, set of all ordered pairs of real numbers, and it is what we set this R square. What is it? Is R square, which is two-dimensional space. Two-dimensional space. Similarly, if I do the Cartesian product of three sets A cross B cross C, which are coming from the real numbers, set of real numbers, then the Cartesian product of this can be represented as the space is R cross R cross R, which is R cube. This is the three-dimensional Euclidean space. Okay, this is three-dimensional Euclidean space, and the points which we get here, the set of ordered pairs of the points which we get here, are the points in the plane, in the plane, like it is coming from the R square, which is two-dimensional space, then these are the points in the two-dimensional space. These can be pointed here easily. Let's say it is A, it is B, and I am pointing out these all these ordered pair in this two-dimensional plane like this. 1, 2, 1, 2, 3, 4, 5, 6. Okay, I have 2 comma 1, 2 comma 2, 4 comma 1, 4 comma 2, 6 comma 1, 6 comma 2. Okay, so I have represented this set, this Cartesian product in the two-dimensional plane like this. Okay, so this is the diagrammatic representation. What? It is the diagrammatic representation of Cartesian product. We can also represent it like this, that I have a set A with 2, 4, 6 and a set B with element 1 and 2, where 2 is being producted with 1 and 2, 4 is with 1 and 2, and 6 is with 1 and 2. So this also can be represented like this too. Okay, so now let's see, if I depict the term like x comma y belongs to R, x comma y belongs to R, then what does this mean? If I write this x comma y, this ordered pair belongs to the relation R. Here by R I mean that is, this is a relation. Okay, it means that x stands in relation R to y. Okay, the meaning of this set, this particular order, is that x stands in relation R to y. Now let's see what is the main definition of relation. What is relation? So relation is R, a relation R from A to B. Let's write it like this. A relation R from A to B is a subset of what? Cartesian product of A and B. That R is a subset of A cross B. This is the relation. We have studied Cartesian product. Okay, so the relation R is the subset of Cartesian product of A and B. Let's see it like this, that I have the relation between x and y as y equals to x square. Okay, and I have the elements in x like 1, 2, 3, and the elements in y are 1, 3, 4, 5, 9. Okay, if I see the relation between them, then let's see it like this: 1, 2, 3, this is x, and 1, 3, 4, 5, 9. Let's first see the Cartesian product of this. What is the Cartesian product of A cross B? X cross Y. X cross Y. It will be 1, 1, 1, 3, 1, 4, 1, 5, 1, 9, 2, 1, 2, 3, 2, 4, 2, 5, 2, 5, 2, 9. Similarly, 3, 1, 3, 3, 3, 4, 3, 5, 3, 9. Okay, it will be like this. And when I talk about the relation that y is related to x by y equals to x square. Okay, then if I put the value of x here, x, what is x is? X here is the independent variable, and y here is the dependent variable. Okay, y is the dependent variable, and see this also, that x here is the domain. What? It is the domain, and y is codomain, and you can say range. Okay, if I put the value of 1 in this, then it will give me 1. Then my very first relation that I got is 1 comma 1. If I put the value of 2, then I got y equals to 4. Then second relation I got 2 comma 4. And if I put the value of 3, then I got 9, which is 3 comma 9. This is the relation that I got in y equals to x square function. Okay, so this relation is the subset of the Cartesian product of A cross B. Okay, so this is the relation that we are going to need, and there are some types of relations too. First is reflexive type. What is the reflexive type of relation? Let's see. So if every element of X maps to itself, that is, if let's say I have an element X which belongs to X. If every element of F maps to itself, then that is if every element is related to itself, that is X R X, X is related to X, then it is said to be reflexive. And if I talk about symmetric, what does this mean? If X is related to Y, then Y is related to X. Holds. This is the symmetric type of relation. And what is type of transitive? Then there is third type of relation, that is transitive. And in transitive, I say that if X is related to Y and Y is related to Z, then X is related to Z. Then this the relationship called as transitive type. Okay, so we have seen all these type of relationship: reflexive, symmetric, transitive. Let's understand by this that if I have the relationship that mod of X minus Y is less than equals to 1 on R. Now I want to know whether this relation is symmetric, transitive, or reflexive. Okay, so let's first check about reflexivity. If I check about reflexivity, then for reflexivity, I need that X is related to X. If I depict here this mod of X minus X is less than equals to 1, which is 0 is less than equals to 1. Yes, it is reflexive. Okay, it is satisfying the criteria. Okay, now let's check for symmetricity. For symmetricity, if X is related to Y, then Y is related to X must hold. Okay, let's say I say that 2 is related to 3, then there is a need that 3 is also related to 2 holds. So for 2 is related to 3, so 2 minus 3 is less than equals to 1. Yes, 1 is less than equals to 1. This is satisfying. And if I check 3 is related to 2 or not, then 3 minus 2 is less than equals to 1, which is also 1 less than equals to 1. So this is also satisfying. Okay, so it also holds symmetricity. It is holding symmetricity, it is holding reflexivity. Now let's check for transitivity. In transitivity, let's say we say that in transitivity X is related to Y is related to Z, then X must be related to Z. Let's say I take example like 2 is related to 3 and 3 is related to 4, then 2 is related to 4. Let's check for this. We have checked that 2 is related to 3 holds and 3 is related to 4 also holds, like this. 3 minus 4, which is also 1 less than equals to 1, it is also satisfying. Now let's check for whether 2 is related to 4 is a hold is holding for this particular type of equation. Let's check. 2 minus 4 less than equals to 1, which is 2 is less than equals to 1. This is not satisfying. It is not satisfying. So the transitivity does not hold for this. Transitivity does not hold for this relation. Okay, so this particular relation mod of X minus Y less than equals to 1 is reflexive, symmetric, but not transitive. It is not transitive. Okay, now we have seen the reflexivity, symmetricity, and transitivity, and there is a relation which is called equivalence relation. Let's see what is it. In equivalence relation, when reflexivity, symmetricity, and transitivity, these are three types of relationships, all three types of relationships hold on a particular relation, then we say that the relation is an equivalence relation. Okay, what I said, when a relation is reflexive, symmetric, and transitive, then I say that the relation is equivalence relation. Okay, let's see by an example. If I say that I throw two dice, by throwing two dice, I am throwing two dice, then what are the possible outcomes of throwing two dice? The possible outcomes we get outcomes. by throwing two dice are 1 1, 1 6, 2 1, 2 2 6, and 3 1, 3 2 3 6, and going on with 6 1 2 6 6. These are the possible outcomes that we got when we throw two dice. Okay, now I want to check, and there is one thing to note, that the ordered pair a comma b, this is the set possible set, say that a is coming from set a and b is coming from b, set b. Okay, to note. So if I want to check whether reflexivity, symmetricity and transitivity, all three of them hold for this or not. If three of them hold for this, then we say that this is an equivalence relation, otherwise not. Okay, now let's check for let's say particularly point a particular point. If I'm check for reflexivity, that has to be x r x, that x is related to x, then we have the elements like 1 comma 1, 2 comma 2, 3 comma 3 to 6 comma 6, where 1 is related to 1, 2 is related to 2, 3 is related to 3, and similarly 6 is related to 6. So reflexivity holds for this. Okay, and what about symmetricity? For symmetricity, I said that x is related to y, then y is related to x. Okay, now let's check this, that 2 is related to 1, that is 2 comma 1. So for this we also have 1 is related to 2, that is 1 comma 2. Okay, and for 3 is related to 1, 3 comma 1, we also have 1 comma 3, which is 1 is related to 3, 1 is related to 3. Okay, so for all types of elements we have their corresponding symmetric relation holds. So it also holding for symmetricity, it is also holding symmetricity. Now let's check for transitivity. For transitivity, I'm taking an example like 2 is related to 3 and 3 is related to 4, then whether 2 is related to 4? Yes, we have an ordered pair 2 comma 3, and we have an ordered pair 3 comma 4, and we also have an ordered pair 2 comma 4, which is like this here. Okay, so transitivity also hold here. So this is, and the throwing of two dice is an equivalence relation because it is holding reflexivity, symmetricity and transitivity too. And how does we denote this? This is an equivalence symbol. Okay, that x is, let's say a is equivalent to b, we are depicting it like this. So in previously we have said that our relation R is from set A to set B. R is related from set A to set B. Then if I'm talking about the inverse of this, R inverse, then what is R inverse is? R inverse is set from B to set A, from set B to set A. Okay. Then R inverse is B comma A, where A comma B belongs to R. Now the point to note here is this. This is the domain and this is the range in the set of in the relation R. Okay, and when I'm talking about the relation R inverse, the relation of R, the inverse of R, then the domain becomes the range and the range becomes the domain. So the point here to note is that the domain of relation R is the range of R inverse, and the range of R is the domain of R inverse. Okay, so this is the basic of relation topic. Now let's see our next topic, which is functions. What are functions? Let's see what our functions are. Functions are basically an expression or law that defines a relationship between variables. What is this? It is a relationship, or you can say it is a rule. It is a rule that defines a relationship between variables. Okay, so in respect to relation, the definition of function we define as a relation f from a to b. Okay, a relation f from a to b, that is a subset of a subset of A cross B is called function if for each A belongs to A, there exists B belongs to B such that A comma B belong to F. Okay, and so here it means that every element of A has an image in set B. Okay, and there is one point to note here, that is no two ordered pairs in function F have the same first element. By saying this, I mean that the image, I mean that the image that an element of A has a unique image in B, has a unique image in B. Or we can say that by first I mean that all elements of set A associate to elements in set B. Okay, associate to elements in set B, and an element of set A is associated to a unique element in set B. What? There has to be a unique element in set B, in set of image. Okay, let's say it by slates. So this, what does this set A here is? The set A is the domain part, and the set B here is the codomain part, and you can say a range. Okay, uh, image, image. Okay, now let's see that we are representing function like f is function from x to y, where f is what? F is the rule or law, and x is the independent function, independent variable, independent variables, and independent set actually, and y is the dependent variable, dependent set, dependent set. Okay, so let's see it by like this. If I'm talking about the area of circle, area of circle, what is the area of circle? It is pi r square. Okay, now let's see it depicted as y equals to pi r square. Here r is independent variable and y is dependent variable, dependent variable, and we can see that it is also a function, it is also a function. Here is the circle, and this is the point, this is the radius in this. By putting the value of the radius we can get our area, which is y. So this is technically a function. For every value of r, for every each value of r, we can get an area, that is y, such that a comma y, that is x comma y, belongs to the function f. Okay, so area of circle, that is also a function, and if I'm talking about the area of the triangle, that is also a function. Okay, so let's see the mapping. Function is also called as mapping. So let's see the mapping, the types of mapping. Mapping is basically of three types, which is 1 onto, and 1 onto, which is bijective, and the basic, you can also call them 1 or injective, onto and surjective or surjective, and bijective, which is 1 and onto. Okay, first we look at 1. What is the 1 function? F is going from A to B, then a function is said to be 1 if different elements of A have different images. Okay, if different elements of A have different images, like I have a set A and a set B. Let's say these are the points in this. Okay, so if different elements of A have different images, like this, different elements have different images in this. This is the domain set and this is the image set. So here we can see that every element of A have different image in the set B. So when this type of mapping happens, then we can say that it is 1 or injective mapping. Okay, now let's see onto or surjective. What does this mean? Onto or surjective, we say that a function is onto if every element of codomain, this is our codomain 2. This is said to be codomain 2. If every element of codomain is the image of some element under F. Okay, this is my A, this is set B. So the function is onto if every element of set B has the image, if the mapping is goes like this. If every element of set A has the image, let's depict it like this. Okay, if every element of set A, sorry, if every element of codomain B, if every element of codomain B is the image of at least one A belongs to A, okay, then we say that the function is onto or surjective or surjective. Let's say about the bijective part. What is bijective? Bijective is when the mapping is 1 1 and onto. When the mapping is 1 1 and onto, let's say it by like this. This is 1 1 1 1 and onto that every element of codomain is the image of some element of A. So it is the case here that every element of A is the every element of codomain is the image of some element under F. Okay, so this is the bijective mapping. Okay, so these are the three types of mapping: injective, surjective, and bijective. Okay, now let's see the composition of mapping. Composition of mapping. By composition of mapping, I say that if f is a function which is going from A to B and g is a function which is going from B to C, then GOF is a function which is going from A to C. Okay, it can be seen like this: f A is going to B by the function f and B is going to C by the function G. Then GOF is going from A to C. Okay, it is the GOF mapping, which is similarly saying that G of FA. Okay, but the point to note here is this, that if GOF is defined, if GOF is defined, it doesn't mean that FOG is also defined. Okay, it may be the possible case that GOF is defined, but FOG is not defined. Not defined. Okay. Now let's see it by this, that I have a function, let's say ux, which is 3x, and another function which is fx, which is equals to x square. Now let's say if I do the mapping FOU of x, which is equals to f of ux, which is f of 3x. So it became 9x square, and u of fx, what does it depict? It is f of u of fx, which is equals to u of x square, and it became 3x square. So from this we can see that f of ux is not equals to u of fx. Okay, so this is the composition of mapping that we use, GOF, FOG. Okay, now let's see an important type of mapping, which is identity mapping. Identity mapping. In identity mapping, when a function f goes from A to A, that is defined as f A is equals to A. What does this mean? It means that function that assigns to each element in A itself is called identity mapping. Okay, that function that assigns to each element in A itself then it is said to be identity mapping and represented by IA or just I. Okay. Uh, so we are as saying that f is going from function from f is going from a to b possess an inverse. The function f possess an inverse if it is what? If it is bijective. If it is bijective. Okay. The function f has an inverse if it is bijective. So by inverse, we say that f is going from a to b. The inverse of this, let's say g, is from b to a. That is inverse of f. Okay. So if I do the composition of these f and g, I got the identity mapping. Okay, like this GOF. If I do the composition GOF, then I got at IA, which is left inverse. And I got this mapping and I got identity mapping on A, left inverse. If whenever I have function is 1 1, whenever our function is 1 1, then we got left inverse by GOF function. Okay, and when I do the composition like FOG, then I got IB, identity mapping on B, that is right inverse. Right inverse. It is when the function f is onto, when the function is f is onto. Okay, so this is all about the identity mapping and inverse. So we mainly use real functions. We mainly use a real function. What are the real functions? The real functions are those ones whose codomain and domain are subset of real. Okay. Whose codomain and domain are subset of real, then they said to be the real functions. Okay, there are some standard real functions. Let's see some of them, like exponential one, exponential function. Let's see exponential function where f is going from r to r and f of x equals to a ki power x, where a is greater than 0 and a is not equals to 1. And here domain is the real number and range is 0 to infinity. Okay, so if I depict it like this, let's say for this one, if a is greater than 1, let's say the case 1. Our first case is if a is greater than 1, then fx equals to a ki power x became uh, less than 1 for x less than 0, equals to 1 for x equals to 0, and greater than 1 for x greater than 0. Okay, so from this we can see that this function increases as the value of x increases. Okay, so the graph of this function, the graph of this function is like this, where this point is 0 comma 1, and this is a graph of y equals to a ki power x when a is greater than 1. Okay, now let's see the case when a is lying between 0 to 1. When a is from 0 to 1, then the function fx equals to greater than 1 when x is less than 0, and equals to 1 when x is equals to 0, less than 1 when x is greater than 0. And at this point of time, the function f is decreasing as value of x decreases. So from this, we can make the graph like this, that this is the graph of y equals to a ki power x when a is lying between 0 to 1. Okay, so this is the exponential function. This is the graph of exponential function when a is greater than 1, and this is the graph of exponential function when a is lying between 0 to 1. Now let's see the logarithmic function. It is also an important function which we use uh, so many times. Logarithmic function. Let's see. Fx equals to log ax. It can also be written as log ax, and x equals to a the power y, and the domain here is 0 to infinity, and the range is r. Okay. For this, we consider the two cases when a is greater than 1. When a is greater than 1, then the y function became less than 0. When x is lying between 0 to 1, equals to 0. When x is equals to 1, greater than 0. When x is greater than 1. Okay. Then the graph of logarithmic function here became like, oh, sorry, it is like this. Okay. This is the graph of log of ax when a is greater than 1. And what is the case when a is lying between 0 to 1? Then the function y became greater than 0 when a is between when x is between 0 to 1, equals to 0 when x is equals to 1, and less than 0 when x is greater than 1. Then the logarithmic graph became like this. Okay. So this is the logarithmic function when a is greater than 1 and a is lying between 0 and 1. Now we also have a function like reciprocal function. Reciprocal function where y equals to 1 by x, and their graph is like this. This is the reciprocal function. We have cubic function too. Cubic function, and the function is y equals to x cube, and it is like this. This is our cubic function, y equals to x cube, and we have square function. Square function which is y equals to x square, and it has graph like this. This is our square function, y equals to x square, and we have trigonometric function. Trigonometric function like sin x, cos x, tan x, and the graph of like sin x, we have when y equals to sin x, then the graph of sin x is like um, this. This is the graph of sin x, and okay. So these are the functions. Okay, what we study here, we didn't just go through with that, but these are the particular type of all those functions. I have already said this, that the area is also a function. The trigonometric graphs, all the types of trigonometric graphs are also functions, logarithmic functions and exponential functions. These are some important functions that we use randomly. Okay. So this is all about relations and functions. In the next lecture, we will study groups and rings and fields. Rings and fields. Okay, thank you.